invite you in to start kindly.
Okay, Chart, you can start anytime.
Okay, so let me introduce today's speaker, and yeah, then we can go from there. Right, so it's a great privilege for me to introduce today's speaker. It's Dr. Philip Amuyunzu Mang'are. It is because he's a key figure in biophysics in Africa at the moment. He's involved with many networks to advance biophysics in Africa. He's currently the Biophysical Society's ambassador in Africa, and also involved with many leadership positions in biophysics. So Dr. Mang'are completed his education at Egerton University in Kenya. Yeah, so he's undergraduate, a master's, and PhD, and he's currently a lecturer in physics at Masinde, Muliro University of Science and Technology in Kenya. So he's involved with a broad network with people in various other countries. He has attended and presented papers for many international conferences around the world. And what his research is focusing on is mainly in electronics, biophysics, and bioacoustics. And I believe today's talk is also going to tie in with that focus. So I'm very much looking forward to this presentation, Dr. Philip, and I'm giving the floor to you.
Thank you very much for that wonderful introduction. Today, I would wish to share with you my experiences with the sounds, particularly animal sounds, and particularly employing these particular sounds in solving a biological problem that has been a big challenge in Africa. The main concern is that many sounds that have been used are those that mimic animals like bats and so on. And these ones are generated using electronically, using what we call the EMR. Now, these EMRs have been investigated. Unfortunately, the efficacy in repelling mosquitoes has been so low. It was therefore important for us to consider the natural sounds of this Odorrana tormota, which is a Chinese frog found in Huangheng Springs, that's in China, and also consider, and that's the male. We also have the Delphinapterus, leucas. This is the belunga whale, sound from the belunga whale, and then the sound from the male mosquitoes. And the main aim was to assess the effect of the 35 to 60 kilohertz synthetic currents. Now, of these particular animals, in terms of spatial activity index to the mosquito and the protection index to the vector. That is in the tropical matted female Anopheles gambiae. Now, as you know, malaria is prone in Africa, particularly in tropical regions, Kenya being part of it, Africa as a whole. It is basically caused by Plasmodium falciparum. This is a protozoa, and transmitted by the matted female Anopheles gambiae. I've used the word haematophagous purposely to show that they require blood meal after mating for egg nourishment. It has been noted that this Plasmodium falciparum is actually the most common and prevalent malaria parasite. And as you know, malaria is responsible for deaths, mortality, morbidity, and even worldwide economic burden. As you all understand, a lot of money in terms of dollars has been spent in order to come up with a lasting solution. But this has not been forthcoming. These are the trends for the malaria cases and even deaths in Africa. You find that it is actually on a declining trend. However, the rate at which the decline is occurring is worrisome, and therefore the need for us to come up with approaches which can actually speed up the reduction in mortality and morbidity. Note that also, we need to, it has been found that the vector, if we address the vector, we will have solved the biggest problem by breaking the chain. When you remove the vector, then you will have actually broken the chain. Now, natural sounds, like in my previous studies at master's level, and artificial sounds that have been reported by Eve from other studies have shown that mosquitoes tend to exhibit phonotactic responses, particularly even other insects. This comes right from the earlier days. Like, for example, when a mosquito attacks you, the first instinct is to kill her, and it vanishes. These, even other animals, even if they are birds, our first option for protection is actually sound. It is in this view that we noted that there was need for us to explore highly potential area that has not been studied. If you look at some of the results that had been shared before, like the use of electronic mosquito repellents, the sound brackets which were used was a band of 40 to 55 kilohertz. Sorry. Now, this yielded optimum repellence of about 68.99%, which was actually what we call the negative phonotactic. Now, if you look at Odorrana tormota, purely an animal sound, and I was the first one to investigate this. Notably, I was able to raise an efficacy of 45.88%. However, these experiments at master's level employed rudimental approaches, but which were not really guided by the World Health Organization and any other protocols. It was a bit rudimental. But it taught us that there is high potential in exploiting these animal sounds. Then we had what we call the winded electronic mosquito repellent. This is a mosquito repellent that was generating ultrasound, which combined with the wind. Why the wind? Wind comes in because it destabilizes that particular mosquito. And that yielded a slightly higher efficacy of 60.7%. Now, maybe I could say something about this topic. Why do we go for the male mosquito sounds? Why do we struggle to go for the synthetic sounds of the male mosquito? The aim is based on the ground that when the mosquito mates, the female mosquito mates, it becomes refractory to the males. And how do they realize that the males are in their vicinity? They use the antenna, which is able to detect ultrasound, because the ultrasound from the male will make the antenna of the female mosquito reflect at the same frequency. In the process, and generally all ultrasounds, they tend to cause nervous stress, and making the animals to avoid the sources. of that particular sound. The male mosquitoes and even the female generate sounds through wing beats. Why do we go for D leucas? That is the beluga whale. These are animals that produce a sound which go to the spectrum of the ultrasonic levels. The same happens to this particular Odorrana tormota. The Odorrana tormota is the male that tries to communicate with other frogs, and because they stay at the function springs, the sound of the waterfall is so high. So to enable them to communicate, they have to raise their frequency above the environment. And that is how they are able to even communicate, particularly during the mating season. That now gives the background for these particular animals. Nothing has been done so far on the synthetic sounds of this particular animal, either singly or in combination. It is very important that we look at what we call the Spatial Activity Index and the Protection Index, which is listed by these particular sounds on the female Anopheles gambiae. Let's look at some of the methodology and the results guiding this particular research. Through the previous researches, it was established that with the Odorrana tormota, this was the same experiment. However, it had stages where you consider the sounds in singly, then you do a combination, and then you do synthetic. So we were trying to develop what we call optimization through either combination and even dealing with the synthetic sounds. Remember, there are other acoustic propagation parameters which were involved, and one of them being entropy. Entropy is disorderliness in that sound. So if you minimize the entropy or the entropic level by making the sound smoother and better, what is the effect? And that's why we had to go to what we call synthesis of these particular sounds. In this research, based on the protocols that had been established, and I've presented these papers elsewhere, we were able to establish an efficacy of 80.06%. This is very high efficacy. And it shows that acoustic sounds become a critical component in malaria control. This is by targeting the vector. And what do we mean by this vector? You look at the behavioral response. Is it an evasive response from the sounds? I mean, is it negative phonotactic? Are they running away from the source? And then the Anopheles gambiae individually yielded 78.41%. That is when you play the male sound of the mosquito, you find that the females will run away at 78.41%. That told us that it is possible to actually look at these things. But we asked ourselves, what we combined the male mosquito sound and the female mosquito sound. And that is what is giving us part 2, where we are saying mixed male A gambiae and the Odorrana tormota, which had given us 80.06%. Unfortunately, the mixture yielded 9.64% efficacy. That means the landing rates were very high. There was more of positive phonotactics, and the size, the Spatial Activity Index was negative. We also decided now What we mix all these sounds, will we generate something higher? Indeed, the sound of D. leucas, that is the D. leucas, the beluga whale, yielded 71.82 alone without combining with anything. But we now decided, can we combine Odorrana tormota, a male Anopheles gambiae sound, and D. leucas to see if there will be enhanced efficacy? Unfortunately, it also gave us 39.26%. Now, what came to our mind was that maybe during this mixing of the sounds, definitely we have what we call the interference, where we have negative, where we have destructive and constructive interference. So, and also the background noises. Therefore, informed us to now move to the next step of trying to synthesize the sounds. I would like us to look at the following clip. This is when the blood meal is what, I don't know if you can see the picture. That's now the video playing. We inclined the blood meal at 45 degrees, but anyway, on the surface, it is greater than 45, but the container at 45 degrees. You notice that there is landing on this particular edge. And this is when we were using the Odorrana tormota sound in single nature. This was the control arm. This is a phyto-Y cage. But this other arm that is being shown now is the treatment cage, where you find that there is a sound source, but it was draughted. There's a sound source here, and the chamber was clean. So, the question point is mosquitoes prepared the blood meal which was not treated with the now look at this situation. When it was at the blood meal is now at 180 degrees. Look at it keenly. You can see the control arm is receiving enough. And where we have some cotton wool is the control. And this is the source of the recorded sound. You find that the area is clean. The landing rates, the mosquitoes avoided that chamber. And those that managed to enter exhibited unique behavior, like squeezing on the walls and so on. All right. Can we look at the last one? This way we were trying to optimize at that particular level. When the meal is upright like that, that is what you are able to observe. You can see some mosquitoes within the chamber. Why? Because we deduce that when you lie the meal in that manner, then you tend to block the sound penetration. And given that ultrasound is weak, it gets diffracted easily. And therefore making that particular blood meal a safe haven for these mosquitoes. That's why they were able to come in. Those are the results from the previous research. Now, ladies and gentlemen, how are we mixing these sounds? I will be able to share screen once more. Allow me to unshare this and show you how we can be able to mix the sounds. Allow me to share full screen. Sorry, it's coming back. Okay. Allow me to open the program. The program unit is called Alphabet. So I can now share full screen. Hey, I don't know if you are able to see that.
No, we see only a dark blue screen. Oh, yeah, no, we can see it. That's fine.
You can see now the bigger one called Alphabet Lab.
Yes, we can. Yes.
Thank you so much. Now, I will use a sample sound to just illustrate how we can be able to mix these sounds. One, you will definitely open the sound wherever it is. I have two sounds, linet A and linet B. That is the sound, which you can be able to play around with. If I need to copy this sound, definitely I'll come to this end and copy this sound. Then open the other sound, which is now linet. After opening this, you will definitely go to edit and then choose mix. The sounds have been mixed. I've used the same animal sound, but you can see the amplitude has been this an oscillogram. The amplitude is enhanced. Why? And even you can see a bit of the redness shows that the gain is higher or beyond. So it is overmodulation. Overmodulation. So it's constructive interference. And now, after combining these sounds through mixing, like for example, we mixed the sound of Odorrana tormota, the sound of a male Anopheles mosquito, and they gave a resultant sound. So that is what I really wanted to illustrate to you. I will be able to show the other aspects later. So allow me to share the other screen and continue as before. Okay. Just a moment. I need full screen. I don't know, you can still be able to see.
Yes, I can see your screen. You can put it to full screen mode.
Okay. Let me redo it once more, sorry. Entire screen, there we are. All right. I've explained how to make the sounds, and I have generally elaborated. Now, how did we generate these synthetic sounds? You know, these sounds have what we call formants, the high energy components of the frequencies. And that is our area of interest. So our question was that mixing the sounds or synthesizing the sounds would yield better results. And I will be able to illustrate the sound with the time. The process which was used, you need to convert the sampling frequency. Remember, when you use a lower sampling frequency, you end up losing some of the components. Particularly, I'm talking to who have done a bit of electronics and analysis. So, with a higher frequency, therefore, you can be able to capture all the details of this particular sound. So, with this generation, after you have opened your spectrum, this is called a spectrum, you will be able to see the pictorial representation of that sound, the image of that sound. Look at these formats. Some people call them harmonics. Of course, we have the normal fundamental. Then you go to a first harmonic, second harmonic, and so on. But what you are seeing here are the harmonics. So once you have identified them, and these harmonics have the way you see them have a meaning. Like at this point, if you can see the cursor, this change, the lowering point here, where it tends to curve, is frequency modulated. And where it is constant, it is called constant frequency. And if you go to animal biology, you will find that the nature of the sound generated, for example, by birds will determine whether it is a navigation, a sonar, a kind of sound, or a hunting sound. Each of them have got a purpose. So as you look at this image, you need to draw step by step manually using your cursor and remove all this background noise. The dark background is as a result of noise or any other sort of interference. So once that is done, you generate a spectrum which we are calling the synthetic sound. Now, once you have this synthetic sound, remember, through optimization, we realize that the 35 to 60 kilohertz is the sound that generates maximum repellence in all areas, whether in combination or in single sound. This is our phytoid cage. This is where you enter the mosquitoes. 50 mosquitoes were released into the neutral cage. And this point here, around XY, is called the decision point, where the mosquitoes have to make a decision, either to go into chamber A or head into chamber B. Indeed, this is a blood meal, and we use the blood from the cow, or Taurus, and maintained the temperature using warm water. Remember, the mosquitoes are attracted using certain cues to this particular blood meal. But whenever you put it, so the blood meal was like an attractant, but the treatment was the sound. I didn't go into the details about this, but we did experiments using 10 to 34 kilohertz, 35 to 60, then 61 to 90. That research of the entire spectrum was done, revealing that the 35 to 60, which was indeed in agreement with other results that had been obtained, evoked optimal repellence. So which software did we use? To synthesize, or computationally, we used what we call the Absoft Lab Pro. This was actually a software that was donated to us for this study, and the sounds of D. leucas were equally donated to us because they cannot be found within our locality. But through our network with the Bioacoustic Society, we were able to get this. The results obtained from Avisov lab were verified using Raven Pro 1.6. So these counts were played, and the Spatial Activity Index established. So these are the various parameters which were observed. You look at the number of mosquitoes that entered the control chamber. Then you look at the number of mosquitoes that went into the treatment chamber, and then you look at NM, the number of mosquitoes that responded holistically. So if the value of psi is negative, then it means the response of these mosquitoes was attractive. That means positive contacts. But if the value is positive, then it yielded what we call repellence or adverse response or negative contacts, as guided by the World Health Organization in their issue of the guidelines in 2013. Then, protection index would tell you how protected the body is. Now, the blood meal mimicked the animal, like a human being or any other vertebrates. So the protection index was calculated using the number of mosquitoes which were landing in the control chamber, and then you look at the number of mosquitoes landing or that landed on the blood meal. That is as per World Health Organization, the year 2013. So this is the device which I have the prototype, the prototype, which we need to patent and eventually put into production. But I believe by sharing this, the way Africa is, we are impeded by economic situation, but this would go a long way in helping the society. So the mean spatial activity indices of all the sounds investigated, we had the sound of Odorrana tormota, synthetic. Then we mixed the sound of male, Anopheles gambiae, and Odorrana tormota. And then we mixed all the three sounds, including the leucas. They all evoked positive psi value, which means it was repellent. The ultrasounds in those areas were repellent. Remember, ultrasound is environment friendly. Why? Because as adults, we are not able even to hear that sound. But you can see mosquitoes are able to detect that sound using their antenna. What about the protection index? Incidentally, remember, the protection index, which was highest, was 80.06, which was evoked by the Odorrana tormota, pure Odorrana tormota. However, after mixing some, we noted that the protection index was lower than even the one for Odorrana tormota. And you can see the frog standing out in terms of the ultrasound and the ability to expel the mosquitoes. And remember, the environment of this mosquito, the Odorrana tormota, is a habitat of these particular mosquitoes, as you know. Let's also look at after mixing and after synthesizing. It is very clear that even if you synthesize these plants, their repellence level was lower than that of Odorrana tormota, which was optimal with a bigger margin. Look at Odorrana, the synthetic Odorrana tormota. It yielded 46.35%. Then Anopheles gambiae and Odorrana tormota, 39.6%. And finally, all the three sounds, 43.20, which was far much below the protection index. And by this, it means more mosquitoes landed on the blood meal compared to those that were being repelled. Scholars, I have to say that the 35 to 60 kilohertz synthetic sounds of Odorrana tormota still recorded the greatest protection index, and the sky due to superior acoustic propagation parameters. And what were these acoustic propagation parameters? It was not in the scope of this particular presentation, but I've mentioned entropy, I'm mentioning maximum energy, acoustic energy, acoustic bandwidth of that particular sound, among others. In summary, we are saying that synthesizing sounds of optimal protection index does not improve the efficacy in the repellence of the female Anopheles gambiae, as shown in that particular graph. So you notice that even the landing rates are actually greater. They are higher. It means they were higher compared to the pure sounds that we had earlier investigated. Colleagues, that is my presentation. Allow me to stop there and just demonstrate the issue of the sounds. Allow me to how you can synthesize these particular sounds. Okay, so I will be able to open a new sound. You just open the sound from the software. Once you have opened, you will come to analyze and you create a spectrogram. Now, this spectrogram shows you the nature of the harmonics and the modulation. So, you may go that route or choose to come back to analyze, edit, and go straight to synthesize and choose synthesize graphically. The choosing synthesize graphically, you will get this kind of a window. So you will come to view and remove the lower one of overall amplitude. Once that is done, you will then be able still to come back and now bring back the spectrogram, and you will draw that particular, those formants manually. So it's a bit laborious, but worthy the task. Thank you very much for your time. That is just a section of what I've been able to do with my team. And we are looking forward to patenting and trying to go to mass production so that we can impact in the society through science. Thank you very much.
Yes, thank you very much, Dr. Mang'are, for a very interesting presentation. It is refreshing to have a presentation on a topic that hasn't been represented before. And this is a very important and very relevant topic for Africa. Thank you very much for that. The floor is open for questions. Please raise your hand if you have a question. Yes, Lawrence, please go ahead.
Are there other species that are responsive or that can basically hear in that frequency range?
Thank you for that good question. You know, we have both species for the mosquitoes and also different species for the animals. But I have to say that we confined our study on the most prevalent in our area, and that is the Anopheles gambiae stricto. But I know Repellency as a species has been investigated though the repellence level had not been established. So that is work for us to continue doing, because this has been an eye-opener that sounds can still be used in the repellents. Now, on sources of sounds, other animal species have been used. Like, for example, the bats. The bats, locally, though people don't like them in their natural state, but because of the production of ultrasonic calls, they have been exploited in what we call the electronic mosquito repellent devices. So they mimic that sound, but not the recorded.
Oh, we may have lost them a little bit. Maybe he's buffering.
Yes, looks like we've lost the speaker. Let's just wait a few seconds.
Well, what's interesting is that the I mean, this might be I guess he's saying that the mosquitoes perceive the ultrasound through the antenna, or if there was it more somatic, like through their body, like we perceive ultrasound through our bodies. I wonder if the mosquito heats up, which is, I guess, the basis of ultrasound therapy. You know, I actually have one. I have an acoustic device that's supposed to repel snakes, because I have a very low tolerance of snakes. So this is very interesting.
Yeah, the role of vibrations in biological systems is extremely interesting.
Yeah.
Okay, I'm not sure if the speaker is able to come back. If not, I would like to encourage the audience to, if you have any questions, please do contact the speaker. I'm sure he'll be happy to answer your questions. Yeah, I'm glad that we managed to hear his presentation until the end. He wasn't cut off too soon. But it was indeed a very interesting presentation. So I think then we can end the meeting here. Thank you very much for everyone's participation. And yeah, please join us again next month. So Lawrence, have we decided on the speaker for next month?
Yes, so next month's speaker will be about brain imaging and neuron mapping inside the brain. Be a colleague from Singapore.
Okay. Yeah, yet another very interesting topic. So please don't miss on that. And I hope to see everyone back again next month again. So thank you very much for attending.
Okay. Thanks, everyone.
You are welcome.
Hmm?
You are welcome.
All right, we'll see you.